Welcome to lecture 24, and we were discussing about regulation. And goal of this lecture will be to obtain an approximate expression for regulation of a transformer. Okay, I will do this. Acha, before that, it is now time as slightly I will review the equivalent circuit, how we are drawing this way, that way with respect to primary side, secondary side. So, it is like this, reviewing quickly, I mean quickly the equivalent circuit. And approximate equivalent circuit, approximate equivalent circuit. See, this was my transformer. Here were my coils, primary, secondary. This is the practical transformer. These are the terminals available to me. Okay. Then, and here will be some impedance connected across the secondary Z2. Now, this can be thought in various ways. One way is, here is your V1. Some deeper look into this equivalent circuit, so that it will enhance your understanding, I hope. So, so what I told, there will be R1 X1, I can show it like this. And then here there will be an E1, because this ideal transformer part is this one, okay? And parallel branch is here, that I am not drawing, as you can easily see that parallel branch will not come in the expression of the regulation. In other words, what I am telling, why it is approximate, we will neglect the no load current, because no load current, which comprises of core loss component of current and magnetizing current, is only about 5% of the rated current, and drop because of that in R1 X1 or R2 X2, they are very small. So, this is the thing, and this is E1, a source of EMF. This becomes a source of EMF as there is a time varying flux, polarity I know, this is my V1. And secondary side, it is like this, there is, it becomes a source of EMF, this is plus minus, that is the dot. So, fine, and here was your R2 X2, and here is your load. This is the ideal transformer primary, this is the ideal transformer secondary. No load and magnetizing I have neglected. So, this is like this. Now, interesting thing is this one, because this portion is ideal, you can view it. I will better tell you one of them only you adopt. Achha, what I am trying to tell, this is same as this thing. sorry, this is load, that is, if you wish you show no impedance on the secondary side, this you punch here, I mean push it here on the primary side, this plus minus, and this circuit and this circuit will be identical, no problem if you solve it. This is equivalent to this, or this thing can be also thought of, although space is less, but I will draw it here. This way you can also think it. You show V 1 here. It means that you are assuming secondary coils have no leakage flux and resistance. All resistance and leakage fluxes are there on the primary side. Many ways of looking at things. This one could also be drawn like this. You can show all the impedance on the other side, that is, here it is V 1, here only you show E 1, you pretend this is your E 1, this part your ideal, and here is another source E 2 plus minus, and here you do not neglect R 1 x 1, but push it here, it will be R 1 by a square, x 1 by a square, and then R 2 and x 2 do not disturb, and then Z 2. This is also correct. And finally, this thing, if you have drawn referred to this side, I think you have got this idea, this is one block. Okay. Also, this Z 2 can be this circuit, this is the circuit we will look at, this circuit can be shown to be, let me use a different color, and I will show it V 1, and here R E 1, this R 1 plus R 2 dashed, then sorry X E 1, and here I will forget about this ideal part and connect S square Z 2. In fact, I could draw it straight away, because we have come up to this only thing magnetizing branch, as you will see it can be because. So, this is the equivalent circuit. Finally, I will be using one of them, you use, always use this one. I am just requesting you, it does not mean that you cannot have other options, either this or that. Similarly, this one means what, and you will show here it is B 2 dashed. Here similarly, this will be shown as, this can be, here I have shown, it can be shown as R E 2 X E 2, R E 2 if I am writing no dashed, it means R 2 plus R 1 by a square, X E 2 is x 2 plus x 1 by a square, and then you say that okay, this is the thing, and here you say Z 2, but here you write E 1 by E 2 is N 1 by N 2, that is strictly. So, it is V 1 dashed. So, this is the equivalent circuit referred to load side, secondary side, and it is the equivalent circuit referred to primary side. Okay. So, either of this or you can live with this, but this is somewhat complicated because complicated in the sense computationally it is difficult. You first know this is your V 2, this is whatever current it is delivering, things like that. Anyway, you know how to handle it. So, now coming to the expression for regulation. So, expression for regulation. So, I will refer to equivalent, refer to primary side, okay, refer equivalent circuit, refer to primary side is this one. Primary side. This will be simply this. RE2, XE2, and here is your load, reflected load A square Z2, and here is your V1. And the voltage here I must write V2 dashed, is not? And we have defined the regulation as magnitude of secondary voltage, that is where I wrote V 2 0, magnitude of V 2 0 minus V 2. So, magnitude of V 2 0 minus V 2 divided by magnitude of V 2 0, is not, that was the regulation, and all quantities here were with respect to the secondary side. What was this? Here was the transformer, here I am measuring all the voltages. Oh, sorry, that is it will be RE1 and XE1. Thank you. So, this will be RE1 and XE1. Okay, this is referred to primary side. Now, come to this, this is the load side. Now, what I do, I multiply both the sides numerator and denominator by turns ratio A, multiply A is equal to N 1 by N 2. If you do, it will be A magnitude of V 2 0 minus A V 2 divided by A V 2 0, is not? A V 2 0 will be nothing but V 2 dashed 0 with no load connected minus A V 2 is V 2 divided by V dash to 0. This will be the thing. With load disconnected, this is open. So, what will be this voltage, whatever will come here, this voltage with nothing connected is V 2 0. That voltage will be simply this voltage reflected. This will be the thing. Got the point? Where V 2 dashed is the reflected terminal voltage when it supplies some load current I 2 dashed. Some people will also draw the approximate equivalent circuit, means this it is there, but this drop, as you can see, it only depends on I 2 dashed. I naught can be neglected in this approximate equivalent circuit. Okay. So, this is the thing you have to calculate. Now, how can I calculate? I will first draw the phasor diagram of this circuit. So, the phasor diagram is very simple. I will start from here. The terminal voltage across the load is V 2 dashed. I will draw. Then I will draw the current. Suppose it is supplying some current I 2 dashed, load power factor angle is theta. Load power factor angle does not change if you multiply Z 2 with a square, A is a scalar number. So, it is like this. Then you can easily see V 2 dash 0 is what? V 2 dash 0, that means with this switch open in this equivalent circuit also, when this is open, V 2 dash 0 will be nothing but V 1. This voltage will come here as there will be no current. I think this point must be understood. So, V 2 dash 0 is nothing but V 1 itself, magnitude of this supply voltage. So, V 2 dashed to this V 2 dashed, if I add these two drops, which I am drawing on a larger scale, so that we understand what we are doing, into R E 1 plus J I 1 X E 1, and you must understand it is not drawn to scale. If this is V 2 dashed, how this can be, but there will be some geometrical thing I have to show, that is why I am drawing in a larger scale. So, and this will be how much? This is V 1, and this V 1 is nothing but V dash 2 0. You must understand this point. So, this angle is theta. Therefore, this regulation means magnitude of V 1, next I continue with this knowledge, V 1 minus V 2 dashed divided by the open circuit voltage V 1, equivalent open circuit voltage. Therefore, I will say, suppose I name these various points, like this is suppose O, let this point be A, this point be B, very simple calculation. See, it is like this. Okay. Then magnitude of V 1 means length O C, this length minus V 2 dashed O A divided by O C. Now, I am writing length, this length minus O A divided by O C, this will be regulation. Clear? So, so it will be like this. Okay, in this page let it be a bit dirty, but you will be continuing without any disruption, that okay, this I have to find out. Now, the argument you listen. The argument is these drops, this and this, both these drops are much smaller compared to this lengths. You must understand, because it is a well designed transformer, R E X E 1 are smaller. Much smaller. Compared to whom? Compared to these voltages, compared to V 1 or V 2 dashed. Do not forget to attach these. These are quite small, although I have drawn very large here, so that some geometrical concept I will apply. That is, in other words, what I am telling, it will be something like this. If I draw it to the scale, maybe it will look like, if this is your V 2 dashed, it will be like this, this. Are you getting? This is where I am making this. So, these lengths are really small compared to this lengths. So, you have got the idea, it will be like this. Now, rest of the thing is pretty simple. Therefore, if these two lengths are small, this angle, suppose I call this angle to be delta compared to V or V 2, then delta will be also small. That is, as I was telling, it is V 2 dashed. I wipe that out, but it is like this. If this be the case, then this delta will be pretty small, because you have added only small thing here and there. Okay. So, delta is small. So, keeping this in mind, is it possible then to get the difference between OC and OA? OC and OA, this difference. So, I will now go to next page and start with this phasor diagram rather neatly. It requires like this. So, what you do, this is your V 2 dashed, this is your, suppose it is supplying a lagging power factor load I 2 dashed, this is theta load power factor, and here once again I will draw larger. So, that, so this is suppose I 2 dashed R E 2, R E 1, and then 90 degree here, and this is suppose I 2 dashed X C 1, and this length is your V 1, and this angle is delta, and I named it as if I remember correctly, O C O A B. So, O C, this I called O C, O A, where is B? This point, like this. Acha, now, knowing fully well that delta will be small, delta small for a well designed transformer, then and this one I have got O C minus O A by O C. Now, by using geometry, I will try to find out this length minus this length. Now, since delta is small, if you drop a perpendicular, these are the extra thing I am doing now. You drop a perpendicular on this extended line here, drop a perpendicular. Say, okay, you, and also drop a perpendicular from this side to this side. Okay. Suppose this I call point M. Since delta is small, then I can say that O C is approximately equal to O M, is not? This length will be approximately equal to this length. Because delta is small, if the angle is small, this arc is this one, if it is a radius of a these two lengths are almost equal, r d theta is equal to d s, this length. Therefore, I can say that O C minus O A is approximately equal to O m minus O A, and O A minus O A is nothing but A m, this length. So, numerator is this length. So, this one is approximately equal to A m by O C. Now, the question is what will be the value of A m? Pretty simple. You know, this angle is theta, this angle is theta, because theta I 2 at 2. Angle between two straight lines is same as angle between their perpendiculars. This line is perpendicular to this and this line is perpendicular to this. So, these two will be theta. Therefore, if you drop a perpendicular from point B to n, then now A m can be written as A n plus of n m, and A n is this length. So, in the small right angle triangles, so it will be simply I 2 dashed R e 1 cos theta plus n m. N m will be same as this length B say q, n m is same as B q, it is a rectangle. Therefore, this will be B q and I 2 dashed R e 1 cos theta plus B q from this right angle triangle is this one is I 2 dashed x e 1, this drop sin theta. So, this will be I 2 dashed x e 1 sin theta and divided by O C, and O C is V 1. Okay. Now, I have converted it to once again voltage thing. So, V 1 I can now invoke upon. So, regulation is now approximately equal to, why I am telling approximate? Because I have used this approximation delta is small and so on. So, regulation is approximately equal to this, and this is the expression we are looking for. Now, what is the use of this expression? Because regulation is so simple, otherwise even without doing mathematics, as I was telling, just energize it with rated voltage frequency in the lab and then connect the load, measure with this switch open what is the voltmeter reading, close this switch with this load present, take the difference of these two voltmeter readings divided by the open circuit voltage, you will give you regulation. Then why I have found out an expression? This is because of the fact the rating of the transformer may be very large, maybe 100 kVA transformer whose current rating is maybe 100 amperes. So, 100 kVA load you will be requiring in the lab to find out the regulation at full load at say 0.8 power factor. That is not available. For example, a distribution transformer which is 200 kVA and it caters power to various consumers, I mean totaling 200 kVA. Can you imagine that load in your lab? No. Therefore, you do simple test, open circuit, short circuit test, get these values, and on pen and paper you calculate this. You ask that, oh, what load you have connected? It is delivering rated current at what power factor? 0.8 power factor lagging. Then on pen and paper calculate regulation into 100 if you want to get percentage regulation. So, you are predicting regulation without actually loading the transformer, that must be understood. Okay? Because open circuit, short circuit test are very simple test. I will carry them out, find out these values, then tell me any load current the transformer is delivering, of course, up to rated current, and at what power factor, you give me these two information, and I will be able to give you the value of regulation, how much voltage will drop. We will continue with this. Thank you.